time. Hello, everyone. Welcome back. This is our last Wednesday lecture. Next week, we are going to have our comprehensive exam. I already put a practice exam on Blackboard. Make sure you try it before Wednesday. Well, you should try it as soon as possible because you have to install. Hi, everybody. Because you have to install a browser, and that browser, if you never used it before, it will block everything else. That means you cannot open Zoom, you cannot open any other applications for your comprehensive exam. And a couple of things to know about your comprehensive exam: it will be multiple choices, it will be random questions, and you might get a different question from the other students. So make sure you work on your own exams. And it's a closed book exam. Do not use other materials, but you can use pen and paper and a calculator. All right, so there's a question. Do you have the similarity score comparing the real exam? What does it mean? I don't understand the question. Okay. All right. What else? Okay, so exam is important. Make sure you do all your homework. Then after the exam, you should work on your project. And that's it. I hope I will be able to see some of you in the summer. If we go back to campus and you're on campus, come to see me if you want. Don't come to see me because of your grade. Your grade will be final, and we will try to submit your grade as soon as possible so that you can enjoy your summer. All right. So today and next week, we are going to talk about web advertisement. And I think last time we talked about some of the web advertisement. Let me just show you here. Cool. All right, so still remember what web advertisement that we are going to talk about? Mainly, we are looking for search engine ads like this. So if you are hosting a search engine, when people are querying your search engine, you want to show some ads based on the keywords so that you can get paid, right? And advertisers can bid for the keywords. For example, if I'm selling hats, I want to bid women's hats. So if someone search for women's hats, please show my ads. And here, this table is to show you that in practice, there are different ways that you can specify the match. You can say, I want to an exact match. You can say, I want to, well, exact match, sorry, here. You can say, I want to have a broad match. That means the search engine can have the algorithm says, all right, woman's head is the same as lady's head. So if someone query for this, I will show you ads as well. Okay, so that's the whole that's the problem that we want to deal with. As a search engine, your goal is to be able to show as many ads as possible and as many relevant ads as possible so that people will click on your ads and you get paid, right? So apparently you need an algorithm to decide which ad you want to show because you don't want to show the entire page of ads. At least in the case of Google, probably show 2 or 3 ads per search queries. And in general, for this web advertisement problem, we are looking for online algorithms. So web advertisement is a multi-billion business. This is a very useful algorithm and application, so pay attention. Online algorithms, classical model of algorithms, all the algorithms that we have seen so far is they often use the entire input to compute for some result, except the streaming data, right? Streaming data, we take a part of the input and we compute some approximate result. But other algorithms like a priori, we all look at the entire data set to be able to count. And these are usually called the offline algorithms. Online algorithms are tricky. Online algorithms, you get to see the input one piece at a time, but at the same time, you need to make some decision along the way. So every time you every time you receive an input, you have to make some decision. And you need to make the decision without knowing the future. This is important. This is the main challenge. So for search, we only know the past queries and current queries. We only know what has been queried so far, and we only know the current query, but we do not know what would be the query later. So this is very similar to handling data streams. Also, one thing to know is an online algorithm cannot always do as well as an offline algorithm. So offline algorithms will be your baseline. If you can beat offline algorithm, yes. But in reality, an online algorithm cannot beat an offline algorithm. So let's look at one example to show you that knowing the future could help. Let's say you're a manufacturer A and manufacturer B. They bid for different keywords. A bids 20 cents on both terms sofa and Chesterfield. B bids 10 cents for Chesterfield. What does it mean? Well, if someone queries sofa and you or Google shows manufacturer A's advertisement and the user click on it, A is going to pay you 20 cents. And it's the same for Chesterfield. So two keywords. For manufacturer B, if someone searches for Chesterfield, you show manufacturer B's ad, and the user click on it, manufacturer B needs to pay you for 10 cents. However, if someone query for sofa, you cannot show B, right? Because B did not bid on sofa. B is very specific. I only care about Chesterfield. And also one complication that we have to consider is both of them has a monthly budget of $100. This means you can only charge B for $100 or A for $100. If they go over their budget, even if you show their ads, they will not pay you. So when we look at the query, Chesterfield arrived, you can display only one ad. Which one do you want to show? Well, usually when you look at the problem like this, an easy solution is I will just show A, right? Because A paid me 20 cents. But there are some complications. You might display A's ad because A bids more, right? A and B, and this is called the greedy algorithm. Greedy. However, if there are many queries for sofa and only a few for Chesterfield, B will never get to spend all the budget because all the Chesterfield got assigned to A, and you would use up A's budget or use up a large portion of A's budget. Then for the remaining sofa queries, you assign to A again until A's budget becomes 0, and you still have some leftover sofa and no Chesterfield. You have no one that you can assign to, right? So in this case, sending Chesterfield to queries to B might increase the overall revenue because both A and B bids on Chesterfield. So without knowing the future, online algorithm may not perform as well as an offline algorithm. But let's look at a concrete example. So here we have some query to add matching problem, and let's call it offline because we will be able to see the entire set of queries. Advertisers, they each bid for keywords sofa, for example, so far 10 cents per impression. Impression means when you show it to the user and the user click on it. And they both have a budget. The budget will be $100 per month. And you do have a set of queries in some month, say September 2015. So you do have the entire month query. In this case, you have in this example, you have 600 Chesterfield and 100 sofa. Your goal is to be able to find assignments of queries to ads or to bits so that you will be able to maximize the profit. Okay, all right, so all the information we need, two advertisers, A and B, and their bits. A bids on 20 cents on Chesterfield, 10 cents on SOFA. Awesome. B bids 10 cents on Chesterfield, and they all have the same budget. All right, without looking at other information, what would be the maximum profit you can make in a month if you're the search engine? Anybody? Great. Chen Yuan says $200. Yeah. So your goal is to use up everybody's budget. Then you're okay. So this is your query. Let's see how we would assign the queries so that we might be able to have $200 for this month. We can start by looking at Chesterfield. Chesterfield, you have 600 of them. So let's assign 500 of them to A to use up A's budget. Right? Greedy because A pays more, 20 cents. So now what are the remaining queries? Well, you have 100 here and you have 100 here. So can you assign this to B? Well, or assign this to B? Well, you cannot assign this to B, right? Because B does not bid on SOFA. You can, however, assign this to B, but can you assign all of them? Oh, you can, because 100 queries to B is 100 times 10, $10. Great. So this means you are going to assign ads to all the 600 queries and 0 SOFA queries, right? Because A already have 0 budget. So the total profit is $110. Good. This is greedy algorithm. Is this your optimal solution? Well, maybe not. Let's look at what would be an optimal solution. The optimal solution is, this is the same from the last slide. The optimal solution is we want to be able to assign queries to bits so that we can generate the largest profit. And the optimal solution is here without really telling you how we compute the optimal solution. But we will have that later in the algorithm part. So in this case, how do we generate the optimal solution? Well, you take SOFA, 100 SOFA, give it to A, you got $10, right? This way you consume all the SOFA queries. All right, 0 queries. Great. Chesterfield, you can still use some of the A's budget, right? Because now you only have A and B, you only have Chesterfield, and you already know their remaining budget. So A has the remaining budget of 90. That means you can assign 450 queries to A. So awesome, used up A's budget. What about the remaining queries for Chesterfield? You can go to B because B also bid for Chesterfield. So you have $15. And this way your optimal solution is $115. So if we compare them, this is your original bid and this is your greedy algorithm, which means you always assign the queries to the highest bidders. And this is your optimal solution. You can see the difference here is that we sacrifice some Chesterfield bid to A and allow us to assign SOFA to A to use up this $100, but we still can increase the profit from B. Cool. All right, so I hope now you are, I hope now you agree. Optimal solution, in this case, really need an offline algorithm that can look at the entire query space, right? Think about an online algorithm that before SOFA queries comes, you only see Chesterfield. How would you know if SOFA would ever come? If there's no SOFA, maybe you just assign everything to A, then you have your optimal solution, right? So this is a difficult problem. So the problem is actually online bipartite matching. So let's look at the problem formulation. We're looking at the matching problem. We want to match queries to ads. And let's look at the simplified version of the problem first. In the simplified version of the problem, you have a bipartite graph. Remember your bipartite graph? You have some nodes on the left side, some other nodes on the right side, right? And on the left side, in our problem this week, is the advertisement. On the right side is the queries. So, and the link between them is the bid. For example, advertiser 1 bids for query, keyword A, and C only. That means when A comes in, oh, and also who bids on A? Number 4 bids on A. So when A comes in, you can either pick 1 or pick 4. Okay. So in this problem, we are going to look for a maximal query in the bipartite graph. And this maximal query, maximal matching has a definition, and I'm going to show you the definition on the next slide. So in the bipartite graph, all edges connect nodes on the left side to the nodes on the right side. Okay, just like what we did before. So what is a matching and what is a maximal matching? Well, in this case, you still have the bipartite graph, but if you look at your both thick lines, this is a match. So this match is 1A, 2B, and 3D. This is a match or a matching, and the cardinality of this matching is 3 because you have 3 matches. Okay, so what does this mean? This means when A comes, you are going to show the advertisement for for 1. When B comes, you show the advertisement from 2. When D comes, you show the advertisement from 3. What about C? Can you show an advertisement? Well, let's look at here. C has 2 links, right? Oh, sorry, C only has 1 link. So when C comes, you can only show 1, advertisement 1. However, you already show advertisement 1 when A came to play, so you cannot show 1 again. The idea is, because this is a simplified version, everything on the left side can only be shown once. And you can think of this as the budget. Right, so each of them has a budget of 1. You can only show them once. So in this case, this is a match or a matching or a match, and the cardinality is 3. And our goal is to be able to find this maximal matching. So this will be the matching that contains the largest possible number of matches, right? You want to be able to match as many ads as possible to your queries. In this example, the maximal matching is when you match A to 4, B to 2. So now you can match C to 1 because you did not match 1 to A, right? And then you match D to 3. So great. Everyone has a match, and the cardinality is 4. This is also called a perfect match, which means all nodes on the graph are matched. And if you have a maximal match, it doesn't have to be a perfect match, but when you have a perfect match, it's always the maximal match, right? Because sometimes you might not be able to generate a perfect match even in the offline space. All right, so our problem is to find a maximal match for a given bipartite graph. And this maximal match would be it's a perfect match if it exists. There actually a polynomial time offline algorithm to solve this problem, and it was invented in 1973. when we still do not have internet. If you're interested, you can take a look at the algorithm. But we are not going to look at offline algorithms. Today, we're going to look at online algorithms because in practice, you will not be able to see the entire graph at the same time. So what if we don't know the entire graph? What do we do? And how well can we do the match? So online graph matching problem. Initially, your problem, this is the problem. Initially, your algorithm is given a set of ads. So 1, 2, 3, 4, great. Then in each round, you have some query terms added to the graph. Every time when a query term added to the graph, it will show the edges between the terms and the ad, and an edge indicates which advertisers has bids on those query terms. At the same time, when you see each query, you have to decide whether you want to either pair the query with an ad or you do not pair the query with an ad. Very simple. All right, let's look at an example. Here you have the ads. Now query A comes in, show you 2 links. What does this link mean? This is a bid, great, buoy. So this means advertiser 1 and 4 bids on A, and you have to choose one. And still remember, here we are consider a very simple case. So your budget is 1 for every advertiser, and they all bid for $1. Okay, so equal bid. That's why all these links are the same thickness. All right, so which one do you want to show? 1 or 4? Do you have any information to help you to know which one is a better choice? Well, no, right? You don't have any information. So usually you would just pick the first one. Say, all right, 1. Now you have the second query. B comes in. So B says 2 and 3 means we can still match a query, but which one do we want to match? Well, let's just always break the ties in the same way. So let's take the earlier one. Okay, so Chen Yuan says randomly, but it's in this case, when you want to break ties, you want to do this in a deterministic way. That means you want to systematically break ties. If you always prefer the ads with a lower number, in this case 2 compared to 3 or 1 compared to 2, you should always do that. This also help you to make your algorithm more robust. Not algorithm, result, so that your result doesn't change very much. All right. So when C comes in, C links to 1. Oh no, now we cannot match any ad to C, right? So then we can only choose this option. Do not pair the query with any ad. When D comes in, all right, so we can still have 3 match to D. What would be our matching in this case? 1, A, 2, B, 3, and D. What would be the cardinality? 3, great. All right, so very simple example, but this is to show you that this is very difficult to make a decision, right? When you only see A, you have no other information to decide what you want to match. All right, let's look at some algorithms. First one is the greedy algorithm. So greedy algorithm for online graph matching problem means you're going to pair the new query with any eligible ad. If there is no ad, you don't pair any queries. So very simple, because every ad has equal amount. So greedy algorithm will just pair any ad. So how good is this algorithm? Right? You always want to know how good is this online algorithm compared to an offline solution or an optimal solution. So how do we evaluate that? We evaluate online algorithm in this case with a matrix called the competitive ratio. For an input I, suppose your greedy algorithm produce matching M greedy, while you have an optimal match M optimal. So optimal match means once you have seen all the input or all the queries and the links, you will be able to find the perfect match or the maximal match. So the competitive ratio is the minimum of all possible inputs I, greedies, cardinality divided by the optimal solutions cardinality. So this actually just telling you that we want to know the worst case performance of the greedy algorithm over all possible input I, right? This is the worst case cardinality divided by the best case when you have all the data set. Okay, so this is called the competitive ratio. And you can also replace greedy algorithm with other algorithm. That's also competitive ratio for that specific algorithm. And we're going to look at them today as well. All right, let's analyze the greedy algorithm. Consider the case that your greedy result is not the same as your optimal result, right? Worst case scenario. Consider the set of Q queries, set Q of queries. And these queries, they are matched in the optimal solution. That means they have an at paired with them, but they are not matched in the greedy solution. Cool. All right. If you look at the example here, again, here's your ads, here's your queries, and the black lines are the matches in the optimal solution, and the red lines are the matches in the greedy solution. All right. So what are the nodes on the right side that are not matched in the greedy solution, but matched in the optimal solution? D, right? Because A, B, C are all matched in both optimal and greedy solution. So your Q set has only one node in this case, that'll be D. And let's look at the other set of nodes. Set A is the set of ads that are linked to a non-matched query in Q. So they could be matched to Q. So let's look at here. So this is the non-matched, this is the Q. And what are the nodes that are linked to Q? Well, 3 and 4, right? They link to Q. So they are linked to Q and they are already matched in greedy. Good. They're already matched in greedy, right? Red lines, red lines. So this is obvious because if they are not matched in a greedy solution, that means you can actually match them to D and you solve the problem, right? So you definitely is going to have a set of A nodes that has links to D, but not matched to D in the greedy solution. When I say D, I mean the Q set. All right, cool. So that's here. This is just telling you that if the nodes in A is not matched to any nodes, you can just pair A with the nodes in Q and you're done. All right, so since ads A are already matched in M greedy, that's our assumption, then we know that the cardinality of M greedy is larger or equal to M, right? Because A is a part of M greedy. Cool. This is the first thing we identified. So the summary so far, what have we done? We look at this graph and we say there are some sets of nodes called Q nodes, some sets of nodes called A nodes. Q are the ones that did not match to anybody in the greedy solution, but matched to some nodes in the optimal solution. and A are the ones that links to Q nodes, but they are not matched to Q nodes. Cool. And we know this, right? Because A is a subset of M greedy. We know that there are at least Q number such as in A. Otherwise, the optimal solution will not be able to match all queries in Q. Okay, so let's think about this. If we want to know the size of Q in terms of the size of, if we want to know the size of A, cardinality or number of elements in the A set, and in terms of the size of the Q set, there's one observation. We know that for every node here, you should be able to find at least one node in A, right? The reason is that all the nodes in the Q set was matched in the optimal solution. So they have a match. And where are this match? Well, this match should be here. Right? You can have more than one edge matched to a Q node, but at least you have to have one. So based on this observation, we know that Q is smaller than A and is smaller than M greedy. Cool. Let's look at Q prime. Q prime is the set of nodes that are matched in the M optimal solution. Okay. And also in M greedy. So it's the intersection between M optimal and M greedy. So M optimal becomes this intersection plus the difference, right? This Q here is a set of nodes that are matched in M optimal, but not in M greedy. So, okay, this is just by definition, we know this. We also know that the size of Q prime is smaller or equal to M greedy because this is the intersection between M greedy and M optimal. Okay, so then we can use M greedy to replace this and rewrite it to this. Now we know the M optimal is smaller or equal to Q plus M greedy. Great, we are almost there. So what would be the worst case of M greedy? Well, the worst case happened when Q is large. And when Q is large, that means what? That means you have a large set of nodes that are matched in M optimal, in the optimal solution, but not in the greedy solution, right? So you want this set as large as possible so that you can have a worst case scenario for M greedy. But what would be the largest Q? Well, if you look at here, Q is bounded by A and A is bounded by M greedy. So we know that the maximum Q will be M greedy. And nice, you already have an M greedy here. You just replace this Q with M greedy. And that becomes this. So now we know M optimal is smaller or equal to 2 M greedy. And this tells us that M greedy divided by M optimal is larger or equal to 1/2. So the competitive ratio of a greedy algorithm for online bipartite matching is 1/2. Right? Pretty cool. So greedy algorithms worst performance over all possible input I give you this. And let's look at one worst case scenario. So worst case scenario, you have A comes in, you say, I want to match 1 and A. You have B comes in, you say, I want to match 2 to B. All right, so you don't have 1, you don't have 2 anymore. Oh no, you can only have 2 matches, right? In this case, your Q equal to A equal to M greedy. What would be your optimal solution? Anybody? Now you have seen the entire graph. How would you want to do your match? Okay, Xuemin says 4. What would be the 4? A to 4, right? D to 2, B to 3, C to 1. Okay, great. Thank you. All right, so if we know this is the optimal solution and we know our M greedy is this, what's your Q set? What are the nodes that are matched in optimal but not in M greedy, C and D, right? So your Q set are the queries with no matching. What will be your A? Your A set will be the nodes on the left side who links to C and D. That will be your 1 and 2, but it's already matched in your greedy algorithm. Okay, cool. So your M greedy equals to 2, your Q equal to 2, A equal to 2, and this is the worst case scenario. And optimal solution looks like this. Optimal, M optimal is 4. Competitive ratio is 1/2. All right, so think about this. We are looking at a very small graph, right? But this is a multi-billion business. That means if we just look at the competitive ratio, let's say our profit could be 1 billion if we used up everybody's budget and we have an offline algorithm. But if you just use a greedy algorithm, you don't have 1 billion, you have a competitive ratio of 1/2, now you have 0.5 billion. Which is also a lot of money, but if you can just increase this competitive ratio for your algorithm, if you can just have an algorithm that have a better competitive ratio than 0.5, you are going to increase your profit, right? So that's what we are going to learn next, and we call this performance-based web advertisement. All right, so let's look at AdWords problem. So this is Google's AdWords, but in general, it all looks like this search engine query ads. So given a set of bids for advertisers for search queries, okay? So you already know this. Some advertisers, they bid for some keywords. And we are going to have a click-through rate, CTR, for each advertiser query pair. So let me give you one example. For example, advertiser could be Honda, and the query could be Toyota. What does it mean? Well, this means if the click-through rate tells you that the percentage of users, when they query for Toyota and you show them Honda ads, they will click on it, right? So this could be pretty high, let's say 60%. Because these two car companies are, they share similar customer segment. However, if you have, again, your query is Toyota and your advertiser is what? Lamborghini, where one SUV will cost you 220K. The click-through rate will be very low, right? Maybe 2%. What does it mean? Well, this means even Lamborghini bids for Toyota, but when people care about Toyota, they see an ads of Lamborghini, they will not click on it. Okay, so click-through rate is important. All right, these are just hypothetical examples. A budget for each advertiser, say a month, they will tell you how much they want to pay. Some limit on the number of ads that can be displayed with each search query. Well, 1 ad, 3 ads, 5 ads. We need to be able to respond to each search query with a set of advertisers. Okay, so when someone issues a query, you want to return this so that the size of the set is no larger than the limit on the number of ads per query, right? If you only can show 3, you pick 3 advertisers. Each advertiser has bid on the search query. They have to bid on the query, or if you show their ad, they are not going to pay you. Each advertiser has enough budget left to pay for the ad if a user click on it. Awesome. Let's look at an example. Say you have a stream of queries arrives at the search engine Q1, Q2, and to Qn. You have a number of advertisers bids on each query. When query QI arrives, your search engine must pick a subset of advertisers whose ads are shown on the page, and your goal is to maximize search engine's revenue. So a simple solution when we are considering this click-through rate, instead of using the raw bid to do greedy algorithm, because greedy algorithm will just choose the highest bid, right? When you have click-through rate, the greedy algorithm can use the expected revenue per click. That would be bid times click-through rate, right? If your click-through rate is 100%, then your bid is $1, then you have expected value of 1. If your click-through rate is 50%, only 50% of the user will click on your ad. 1 times 50% is 0.5. Okay, so instead of using your raw bid, you can just use bid times CTR. And also we need an online algorithm. So let's look at an example. So the AdWords, they actually just add this click-through rate, but it was very, very successful. Advertisers, this is their bids. They all have their own click-through rate, 1%, 2%, 2.5%. This can be from historical data. And the expected revenue for each of them would be 1% times $1, 2% times 0.75, and so on. If you sort it by this, you have a new number that your greedy algorithm can use, right? You can always choose the one with the highest bid times CTR rate to show. However, still the same problem. This is exactly the same like what we did for the greedy algorithm. The only difference here is we add this click-through rate. And we still have two complications. First one is this process does not consider the budget, right? Greedy, you don't look at the budget. Click-through rate is often unknown. Each advertiser has a limited budget. So this is the budget constraint. Each advertiser has a limited budget, and search engine guarantees the advertiser will not be charged more than their daily or monthly budget. So we need to be able to take this into consideration. The second complication is the click-through rate. Before we talk about this, let's take a 10 minutes break. Once we come back, we can continue. And if you have any questions, feel free to post them in the chat. I will answer them when I come back. All right, people, I'm back. Let's continue on the web advertisement. So we are talking about this click-through rate, right? We are talking about with a greedy algorithm, you always pick the highest bid. And with the click-through rate, you want to calculate the expected value of a bid so that you can pick the one with the highest expected value. So here, advertiser 1 bids $2, but the click probability is very low. Advertise 2 bids for $1, the click probability is much higher, right? 50%. So all this click-through rate is measured historically. And if you look at this, the expected value for the second bidder is actually what? 0.5, right? 0.5 times 1. The first one is only 0.2. So for a greedy algorithm, you will always prefer the second one, right? Higher expected return. How do you measure this click-through rate? Well, usually it's measured historically, but it's a very difficult problem. Historical measure is actually not a difficult problem because you just do all these countings, map reduce, what else? All these things that we learn that can help you count very fast, right? But this is a hard problem because you do have exploration and exploitation problem that you have to deal with. Exploit means if you see some click-through rate, someone has a really high click-through rate, you can just keep exploit it, right? You just use it again and again and again. But at the same time, when you are using one with a high rate, that means you are sacrificing the opportunity to try new queries, new query and bid pairs, and that's your explore. So explore means should we try a brand new ad to get a better sense of the click-through rate, right? So sometimes people will just put maybe 80%. I'm making up these numbers, 80% to do exploit because you want to have a steady income. You just keep using the one with high click-through rate, but you spend 20% of your queries to explore for the new query bid pairs that you do not have that much historical data, right? This way you might be able to identify someone with high click-through rate. All right, let's look at the greedy algorithm again. In our setting, we do have a very simple environment. There is only one ad for every query, right? The budget is 1. All advertisers has the same budget B, and in our case, it's 1. All ads are equally likely to be clicked. We did not consider the click-through rate. Value for each ad is the same, 1. And greedy algorithm is the simplest solution. So for a query, you just pick any advertiser who has a bid for that query and you're done. And we know that the competitive ratio of the greedy algorithm is 1/2. So just to remind you again, A comes, you pick 1. B comes, you pick 2. C, cannot pick anything. D, you cannot pick anything, right? So let's look at other poor scenarios for greedy algorithms. 2 advertisers, A and B. A bids on query X, B bids on X and Y. Both of them has a budget for $4. Great. Query stream comes. What would be your worst case scenario? X comes, you give it to B. X comes, you give it to B, right? Remember, we deal with ties in a deterministic way. X, B, X, B. Then when Y comes, you cannot assign Y to any of the bidder because A does not bid for Y and B has a budget of 0, right? Because 4, 1, 2, 3, 4, you use up B's budget. Optimal solution will be A, B, 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 B. If you get lucky, greedy algorithm might also give you this, right? So for example, if greedy algorithm always pick A over B when there is a tie, For X, you just assign it to A, B, 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 B for Y. So you have $8. So this is a great case for a greedy algorithm if you pick A first. But remember, when we are looking at the competitive ratio, we always care about the worst case scenario, because you don't get lucky every time. All right, so competitive ratio is 1/2, and this is your optimal solution. And this is actually the worst case. And just remember, greedy algorithm is deterministic, and all other algorithms that we're going to talk about today is deterministic. That means it always resolves your draws in the same way. So if we look at greedy algorithms with non-equal bits, so all the previous examples are equal bits. Now we have unequal bits. Maybe you do have click-through rate also. So greedy algorithm will assign the query to the highest bidders who still have the budget. So here's one example. You have two bidders, A1 and A2. They bid $20 and $10. The budget for B1 is 40 for, well, sorry, the budget B1 for bidder A1 is 40. The budget for bidder A2 is 50. All right. So when query comes, this is the remaining budget for A1 and A2. First query Q comes. We assume that you always resolve tie by in favor of A1. So first query, you assign it to A1. Well, why do we assign it to A1? Because this is a greedy algorithm and A1 bids what? $20. Right. You assign it to the highest bidder. Second query comes, you assign to the highest bidder again, greedy algorithm. So remaining budget is 0, A2 is 50, comes assigned to A2 and A2. Okay. So this is a greedy algorithm, how greedy algorithm would work. So if you look at here, how do you make the decision for the query assignment? Well, first you look at the bid. You always assign it to the highest bidder. Second, you look at the budget, right? When here, when you have this query comes, you still have $20 for A1, so you assign for A1. Now, when this query comes, A1 has 0 remaining budget, so you're going to assign it to A2, right? Pretty simple, greedy algorithm. Now, the real algorithm that we are going to talk about is the balance algorithm. This is a very cool algorithm that helps us to improve the competitive ratio by a lot. So in the balance algorithm, for each query, we are going to pick the advertiser with the largest unspent budget. So this makes sense, right? Because your goal is to be able to spend out everybody's budget. So if someone still have large budget, let's just spend it. And in the balance algorithm, it also breaks ties arbitrarily, but also in a deterministic way. That means if you always prefer A1, you always prefer A1. Okay. All right, let's look at some examples. For the balance algorithm, you have two advertisers, A and B. A bids on query X, B bids on query X and Y. Both have budget of $4. Query stream comes in. What would be the balance choice? The balance choice would be, okay, you assigned it to A. First one, you assign to A. And let's just write it here. So this is the remaining budget, $4, $4. When the first X comes in, What would be A's remaining budget? Anyone? $3. Great, thank you, Bui. And B's remaining budget is 4. So now we have the next X. Do we have a tie? We don't, because 3 is smaller than 4, right? 4, B has a larger unspent budget, so we just assigned it to B. Cool. Now we have a tie, so if you see another X, we always prefer A. 2, 3. Now you have another X comes in. You don't have a tie. B has a larger unspent budget, so you assigned it to B. Now you have Y, 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 Y. What can you do? You can only assign it to B because A did not bid for Y. Great. So in this case, you spend out all B's budget. So 1, 2, 3, 4, and you spend half of the A's budget, 1, 2. So the competitive ratio in this case, if this is the worst case scenario for a balance algorithm, you have what? 1, 2, 3, 4, 5, 6, 6/8. Okay, but remember, this might not be your competitive ratio because we don't know if this is the worst case. Okay, it could be that balance algorithm just get lucky. But in general, your balance algorithm on 2 advertisers has a competitive ratio of 3/4. So this is huge. Your greedy algorithm only have 1/2, right? If you have $1 billion instead of having 0.5 billion for your profit, because of the competitive ratio is 0.5, now you have what? $0.75 billion. That's a lot. 50% increase. All right, let's look at another balance example. 2 advertisers bids on a query queue, A1 and A2. Their bid is $20 and $10. Their budget is $40 and $50. We assume ties are broken in favor of A1. All right, let's start. Remaining budget, 40 and 50. The first one comes in. Who should we assign the budget? Who should we assign the query to? Remember, the balance algorithm always look at what? The remaining budget. So it will be A2, right? And $10, so A2's remaining budget is 40. Now you have a tie, and we say we always broken the tie in favor of A1. So let's go with A1, so 20, 40. All right, so this is winning. We want to assign it to A2. Again, much larger than A1, so A2. Now you have a tie, A1, A2, A2. Okay, so this is your balance algorithm. That you do not look at the bid, you look at the unspent budget. But let's analyze this simple version of balance to show that we can achieve that competitive ratio. So consider a simple case. You have 2 advertisers, A1 and A2. Each of them has a budget B, so the same budget, larger than 1. Let's say your optimal solution will be able to use up both of them's budget, so the total profit will be 2B. Okay, your balance algorithm must use up at least one advertiser's budget, right? The solution of the balance algorithm, because your optimal solution can use up both of them. So let me just write it here. Let's say these are the budget. At the beginning, you have B remaining budget, you have B remaining budget. This is A1, This is A2. When you start to assign queries, you start to use some of the budget, use some of the budget, some of the budget. Okay. And we say that in the optimal solution, you can assign queries to A1 and A2 to use up everyone's budget. Awesome. So in the balance algorithm, the only possible solution is you have to use up at least one of them. Because if you look at here, let's say in a case that you do not, let's say balance algorithm stopped, you cannot assign any query anymore, and you only use up some of A1's budget and some of A2's budget. Okay, what about the remaining queries? You still have a lot of query comes in because you have many empty budget, you have many remaining budget that you can spend. So since in the optimal solution, all the queries can be assigned to either one of the advertisers, that means all the remaining queries can still be assigned to someone, right? So let's say they can still be assigned to A1. You just assign to A1. Okay, assuming you used up A1's budget. Can you assign more to A2? Well, maybe you cannot, because maybe the remaining queries can only assign to A1. Let me just give you one more example. Let's say A1 bids for query the keywords. What would be a good keyword? A1 bid for car, and A1 bid for boat. A2 bids on cars only. Okay. So originally, if we want to use A1 and A2's budget, we just assign all the boat query to A1. And we assign some cars to A1 and some cars to A2. Then we are done, right? That means if one query costs you $1 and A2 has $100 budget, A1 has $100 budget, you might have what? 50 boats and 150 cars. Okay, are we good? So in the optimal solution, you are going to assign 50 boat to A1, 50 cars to A1, and 100 cars to A2. Okay, optimal solution. But in some cases, if we are not lucky in an online scenario, you might assign, let's say, 100 cars to A1. Then how many cars can you assign to A2? How many queries can you assign to A2? Anyone? Oh no. Did I lose everybody? Let me do this again. 2 advertisers. Okay, so 2 advertisers, A1 and A2, they all have $100 budget. Each query is $1. So when we say optimal solution, we'll be able to use up everybody's budget. How many queries in total do we have? 200. Thank you very much. So 200 queries. And assume that we have 50 queries for boat, 150 queries for cars, for car, and A1 bid on boat and car, A2 bid on car. In an optimal solution of line result, how would you assign them? How would you assign the queries to use up everybody's budget? So this is A1, this is A2. Anybody? Have you used up everybody's budget by looking at these queries? All right, thank you, Bowie. A1 got, well, no, A1 bids for cars and boat. So it's the opposite. A1 got 50 boats and 50 cars. And A2 got 100 cars, right? This way you used up everybody's budget. Good, optimal solution. And let's look at other solutions. Let's say Bayes' algorithm or any other algorithm. So for any other algorithm, you would be able to use up at least one of the advertiser. For example, you can use the, let's say if you assign 100 cars to A1, you used up A1's budget. Then what can you do for A2? Well, 50 cars. Can you assign both to A2? No, because A2 did not bid for cars. Good. And let's look at a different scenario. So if we don't assign 100 cars to, if we assume that at the end of the algorithm, we cannot use up either one of the advertisers' budget. Is this possible? Okay. So in this case, we can first assign 50 boats to A1 or 50 cars, doesn't matter. So let's say 50 cars to A1 and another 50 cars to A2, right? Because A2 can only take cars. Can we continue? Can we do more assignment? Well, yeah, because we still have 50 cars and we still have 50 boats, right? In this case, we can either assign boats to A1 or cars to A1. Online algorithm, we do not know about the future, so we'll just assign them randomly or in a deterministic way. So because your optimal solution will use up both of the budget, your Bayes algorithm or any online algorithm can use up this, at least one of them. And the other, you might leave the other one, have some remaining budget. All right. So this is just to tell you that if not, we can allocate more queries to use up at least one of them's budget. Let's say we assume the Bayes algorithm used up A2's budget, but allocate X query fewer than the optimal. What does this mean? Well, this means your total revenue for the Bayes algorithm is to be 2 times B minus X, right? Allocate X queries fewer than the optimal, and 2B is the optimal revenue. And let's look at the competitive ratio in the worst case. So look at the Bayes algorithm. You have A1 and A2, and you have your budget. And the blue ones are the queries allocated to A1 in the optimal solution. And the green one is the queries allocated to A2 in the optimal solution. And we do not know if A1 can take green ones also, or A2 can take blue ones also. We do not know for now. But for the Bayes algorithm, optimal solution would be 2B, right? For the Bayes algorithm, assuming your Bayes algorithm gives a revenue of 2B minus X or B plus Y, looks like this. So what does this tell you? Well, you used up A2's budget because these are all the queries that you have assigned. But for A1, you have X queries that you cannot assign to A1, okay? So what does this tell you? This tells you that this part of the blue queries, you can assign it to both A1 and A2, but for this green queries, you cannot assign to A1. You can only assign to A2, but you cannot right now because you already used up A2's budget, okay?
So the remaining profit for the balance algorithm in this case is B plus Y, right? Over 2B minus X, because X plus Y equal to B. So that's here. Are we good? This is important. This can be confusing, but if you just follow me, you should be okay. All right. So unassigned queries can only be assigned to A2, so that's here. Our goal is to be able to show the relationship between X and Y so that we will be able to have some idea about the relationship between X and B. So we want to show that Y should be larger or equal to X. Let's look at two scenarios. First scenario, less than half of A1's queries got assigned to A2. Okay, so that's here, the blue one. So we say less than half. Well, if this is less than half, that means the blue part here is what? More than half, right? So Y is larger than B over 2, and X plus Y equal to B, so we know Y is larger or equal to X. Great, we show that for case 1. Okay, so remember case 1 is smaller or equal to half of A1's queries got assigned to A2. Let's look at the second scenario. Again, this is the same from the last slide. And our goal is to show Y is larger or equal to X. Scenario number 2, when you have larger than half of A1's query assigned to A2. Could it be possible? Well, yes, if you look at here. You have more than half of A1's blue query got assigned to A2, and this is smaller than half, but you could also have some green ones here, right? So we don't know. In this case, we still want to understand the relationship between X and Y. So let's consider the last of A1's query when we assigned it to A2, the last of the blue one. So when we assign this last of the blue one to A2, A2's remaining budget should be larger than A1's remaining budget, right? Because this last query can be assigned to A1 and can be assigned to A2, but we assigned it to A2. The reason for balance algorithm, there's only one reason, is the remaining budget of B2 is larger than the remaining budget of A1. Okay, great, so we know this. Second, we know that the remaining budget for A2 is smaller or equal to B over 2, half of the budget, since this is what? This is the last of A1's query assigned to A2, the last one. And the case 2 is saying that larger than half of A1's query got assigned to A2. So larger than half, and you are the last query, so at least half of them already assigned to A2. So the remaining budget of A2 will be smaller or equal to B over 2, right? Since at least half of them already assigned to A2. Put all this together, we know that B1 is smaller or equal to B2 and smaller or equal to B over 2. So X or B1 as the A1's remaining budget, it's smaller than B over 2. And since we know X plus Y is B, this tells you what? A is larger, or Y is larger or equal to X. So awesome. We show this again for the second case, right? Two cases. When smaller or equal to half of A1's query got assigned to A2, or when you have larger than half of A1's query got assigned to A2. This means the minimum balance revenue would be 3B over 2. Why? Well, because balance algorithms revenue is minimum when X equal to Y, right? When X is the largest, when you have the largest unspent budget for A1, when X is the largest, which is B over 2, and Y will be the same, B over 2. So B over 2 plus B will be 3B over 2. And this tells you that the competitive ratio for a balanced algorithm in this scenario is 3 over 4. 3 over 4 because in the optimal case, optimal solution has a revenue of 2B. Comes 4, so 3 over 4. Awesome. We just showed the competitive ratio for the balanced algorithm. In this case, is 3 over 4. But in general, for balanced algorithms with many bidders, not just 2 bidders, in the general case, the comparative ratio for the worst case scenario for balance is 1 minus 1 over the Euler number. It's approximately 0.63. And people have shown that no online algorithm has a better competitive ratio for this balanced algorithm. So let's look at some examples of the worst case that will be able to give us this ratio for many bidders. So worst case for many bidders, read this paper, please. This is the balance paper. You have n advertisers. Each one of them has a budget B. And the query, you have n times B queries. And all these queries will appear in n runs, and each run will have B queries. Okay, so you have n times B queries. So in each run 1, the only bidders, the bidders are A1 to AN, everybody bids. Run number 2, A1 does not participate in the bid, so you have A2 to AN. Run number I, you only have AI to AN. Okay, so every run you are losing one bidder. So optimal solution is easy. For the first round, since A1 is bidding, this is the only run A1 is bidding, right? So you're going to assign all the queries, B queries in this round to A. Then you use up A's budget, right? Second round, you don't have A1 anymore. First, A1 did not participate in the bid. Second, you already used up A1's budget. And here, you want to assign all queries to A2 because this is the last round that A2 has participated in the bid. So you assign it to A2, and then you could do this over and over. For round I queries, you just assign it to AI, right? And in this case, each round, you are going to have B queries, you are going to have B revenue. Since you have N round, you are going to have N times B revenue. Okay, optimal solution used up everybody's budget. However, for your balance algorithm, it's not that pretty. If you look at your algorithm for balance, it will assign each queries in run 1 to every advertisers equally, since it is going to look at the bids, the remaining budget, right? It will prefer bidder with the largest on remaining budget. For Q2, it will divide the query equally to the remaining bidders based on their budget as well, and so on. So let's look at the example. Let's look at the graph. It will be easier to understand. So this is the balance algorithm. Round number 1 will look like this. What is this? Well, run number 1, you have B queries, right? For your balance algorithm, let's say you always break the tie by choosing the lower number advertisers. So when you start, it looks like this. And in this first query, query number 1, who do you want to assign? Well, everybody participated in this, has participated in this round. So 1 is here, right? A1, you break the ties. Second query, you look at the remaining budget. Now A2 to AN has the highest remaining budget. So you break the tie by assigning it to A2. Then the next query, go here and you equally assign to everybody. Then you still have, if you still have enough remaining queries, come back to A1 again and do this. So this means for the B queries that you can have in this round, you are going to equally distribute them among all the advertisers who has participated in this round. This way, everyone get a piece of B, and you have N advertisers participated, so everybody get B over N. So this is B over N. What about the second round? Well, second round comes, now A1 does not participate in second round. So it's obvious that you are going to lose your profit, right? This much. Because A1 will not bid anymore. Now, how are you going to assign your bid? Well, queries again. You have B queries in your second round, and you have how many bidders? You have A2 to AN, so you have N minus 1. And you do the same thing based on the remaining budget. You distribute the queries, so it's everyone got B over N minus 1, right? Third round, you cannot use this anymore because A2 doesn't participate, and this yellow part becomes B over N minus 2 because you only have N minus 2 bidders, and so on. Okay, so when do we stop? Well, we actually stop when your last bidder is full, right? That means many people are full. You cannot allocate any queries, or you cannot find budget to allocate any queries, or the advertiser who has the remaining budget, they did not participate in that round. So eventually the budgets of higher number advertisers will be used up. Let's say J is the approximate round when all advertisers are out of budget. Okay, they don't have any budget, even if they participate in the round, or they do not bid on the remaining queries. So how do we find this J? Okay, so this is the same from the last slides, just to remind you. Let's say in the last round, the last bidder used up all the budget, B, right? Which means the last bidder's budget will be larger than B. Well, the allocated query to the last bidder. So what is this? This B times 1 over N is the allocated queries for this bidder in round 1, right? Here, the blue one. And what is this? B times this is the allocated query in round 2 and round 3 and so on until the last round, so that the overall assigned queries for this last bidder will use up all the budget for this bidder. Okay. So cool. Now we have this. If we can have this, well, we can just simplify it. We have a 1 here. Now we only need to be able to solve for J. What would be our J? Well, Euler, our old friend Euler, showed us that when your K gets larger, this number series approaches log EK. Okay, so log K. And this means we can use this and this to replace the number series here. So how does it work? Well, log En is this, right? 1 plus 1 over 2 plus 1 over 3 plus 1 over N. How do we know that? Well, from our old friend Euler. And what is this? Well, this is 1 plus 1 over 2 until 1 over N minus J. Okay. What does it mean? We are taking the difference of this. Well, this means this all cancel out, right? Cancel out. Then you have something like this. So with this Euler's method, we are taking this equation, we convert it to this, and we removed B. We cancel B out. So we want J such that this equation would work, right? If we solve this equation, we will be able to solve for J. And in this case, if we solve it, we know that J equal to N times 1 minus 1 over E, right? It's very simple. You just take log N over N minus J, right? This is the left side. And the right side is log E. And you say this equal to E, and then you solve for J. And we know that J becomes this. So this is the last round that we can assign queries. And since every round we are assigning B queries, so the approximately total revenue is B times J. That would be B times this number. And what will be our competitive ratio? Well, competitive ratio, we know in the optimal solution, you have Bn, right? Every run you have revenue of B and you have N run. So B times N. So cancel out. Competitive ratio for your balance algorithm is 1 minus 1 over E. All right, cool. We just showed this. Very easy. All right, general version of the problem. But in the previous examples, we showed that everyone has the same bit, right? So balance algorithm works very well when your bits are 1 or 0. Either you bid or you don't bid. But in practice, your bits and budget can be arbitrary. In a general setting, when your bits and budget can be arbitrary, your balance algorithm can perform poorly. So how do we solve this problem? Well, let's say we look at two advertisers, A1 and A2. A1 has a bid 1, A2 has a bid 10, budget 110, budget 100. Consider that we see 10 instances of Q. Your balance algorithm is going to choose A1 because A1 will always have the largest remaining budget, right? Because the bid is so tiny compared to A2's bid. And the total revenue will be $10. And this is because we are in favor of advertisers with a large remaining budget. However, in this case, your optimal solution earns $100, right? If you assign every one of the bid to A2, you have $100. So what's going on here? Why do we have the same competitive ratio? Well, this is because the bids and the budget are arbitrary, right? Not like in our previous example that everyone has the same budget and they have the same bid. So how do we improve this algorithm? Well, very simple. We want to bias our choice of ads, not just taking into account the remaining budget, but also in favor of the higher bid. We want to also consider the fraction of the budget remaining, not the absolute number of the budget. Okay, because you can have arbitrary numbers of budget numbers. So we bias toward using some of each advertiser's budget, and this is more risk averse, which means we do not want to leave too much of anybody's budget unused in terms of percentage. So how does the generalized balance algorithm works? Very simple. Consider a query Q, a bidder I, the bid is Xi, right? Let's say $10. The budget is BI, let's say $200. And the amount spent so far for this advertiser, say $50. We first calculate something called a fraction of budget left over. This is very simple. You just take 1 minus spent V versus your budget. Right, this is the percentage that you already spent. So 1 minus that, this is the remaining fractions of your budget. Then we're going to use a function, this psi function. This function for a query is the bid times 1 minus e to the fraction. So one thing that's very important to look at is in this function, we consider bit, because if you have larger bit, the result of this function will be higher. You also consider the fraction of the budget. If you have a large amount of unspent budget, this will be higher as well. And when a query comes, we are going to allocate queries Q to bidder I with the largest value of this psi function, and you are done. As far as why do we come up with this? Well, I did not come up with this. You should read the paper to understand it. But it's similar idea as in that previous example when we are trying to prove the competitive ratio for the generic balance algorithm. But the takeaway here is budget and bit all in the same function. And it can achieve the same competitive ratio as the balance algorithm we saw seen, the first version of the balance algorithm we have seen. All right, let's look at one example before we go for today. So in this example, you have two bidders. First occurrence of Q, you look at the fraction of B1 and B2, and it's 1, right? Everybody, they do not use any of their budget. So psi Q is this, and it's for A1 is $1 times this, so it's this 0.63, right? What is 1? 1 is the bit. What is this 1? This is a fraction of unspent budget. For B, okay, so bit is 10 and fraction is 1, so B is 6.3. Then we're going to assign Q, first Q, to A2. Okay, good. All right, and your psi Q will decrease for your second bidder because the remaining unspent budget is getting smaller and smaller and smaller every time when you start to use its budget, but it's only for the next 9 instance. This will be still larger. This means you're going to assign all the queries to A2, right? For the 10th one, the remaining fraction of budget of B2 now becomes 1/10. So psi 2 for Q is 0.95. It's still larger than 0.63 for your A1 because it doesn't change. So the 10th query is still going to A2, but after the 10th query, we have spent all A2's budget. Additional queries will be awarded to A1. In this case, the total revenue for 10 queries Q will be $100. Okay, so this generalized balance algorithm can help us to bias toward higher bit and also take into account the fraction of the remaining budget, just relying on this psi function. So additional observations for algorithm we covered in this lecture. The algorithm we described do not take into account the possibility your click-through rate can be different for different ads, or you can consider that by generate that expected number and modify your psi function, right? Instead of having a raw bit, you can have an expected bit, expected revenue. Also, you can consider historical frequency of queries to predict for the future frequency. So get you some information about the future that will help you to make decision. So some AdWords aspect not in our model, your matching bit and searching queries. Oh, we're out of time. All right, I have 2 more slides that I can tell you on Monday, but that will be it for today. And I'm going to have my last office hour today in 10 minutes. If you want to come to my office hours, you can come. If you don't have to come, but make sure you work on your assignments, prepare for your exam. It's not easy. You only have limited time to pick the correct answer. So make sure you study very, very well. All right, then I'll see you on Monday. Read your textbook, read your slides, work on your quizzes, homework assignments, and have a good weekend, guys. All right, see you all in 10 minutes if you want to come to my office hours.
挺划算的。
All right, I'm back. Any questions, guys?
Hey. I have a question regarding the final exam or the comprehension exam.
Sure.
I am pretty nervous about like the time management aspect of it, especially since there will be calculation problems. I find that if like they're similar to what we've been seeing in the quizzes.
Oh
you know,
no, it will not be that much calculations. So the important part is to understand the concept, not the calculation. It will have some calculation, but it will be minimal. That means if I have calculations in the exam, those will be if you do well in the quiz, you should be able to get those points. And it will be very simple calculation.
Okay.
You should be nervous. Don't.
I am very nervous.
Don't make me. So you should be nervous. That means you should be able to explain all these algorithms. All the algorithms that we covered in class. You should be able to explain how does it work and the benefit of the algorithm. And when we have, like in the streaming, right? When you have an algorithm, I will not actually ask you how the algorithm works because I think you should know that. But I will ask you about, all right, if we know some of the, if we know how the algorithm works, what are the details that you have to care? It's like in the practice exam. So if you can explain the algorithm to other people, you shouldn't have problem scoring.
And then
in the exam.
I guess my other question is, are you close to being done with coming up with the questions for the exam?
So my goal is to have multiple sets of questions.
Oh, okay.
So that people might not get the same questions. The basic idea will be the same and the difficulty will be the same, but just to make sure that minimize any cheating in the exam.
However, like in terms of the number of the questions, have you
It will
decided?
be 40 questions.
Okay, that's for sure.
Yeah.
What about the duration of the exam? Because I think that was an estimate.
Right. So we'll probably go with 30 minutes.
Okay.
Well, those questions are not the questions that you have to think too much.
No way.
Either you know or you don't know.
30 minutes for 40 questions.
Yeah.
Wow, that's
It's multiple choices. I'm not asking you to write essays, right?
but there are many, there are a
can't
lot of
read that
traps.
fast.
In multiple choices, we have to avoid those traps, so we have to be careful.
You have to be careful, or you don't have to spend a lot of time.
So are those questions mainly about algorithms or those that we need to memorize?
Give me an example of memorizing stuff, and I can tell you.
Well, hold on one second. Let me browse some slides.
For example, I will not ask you which of the following choice is the equation of cosine similarity, right? That doesn't make much sense.
You
I
can
don't want
ask
you to
us
remember.
that. It's okay.
I don't want you to remember that. But I might ask you questions like, hey, now we are using LSH, and look at this LSH similarity and probability chart that we did in class.
Yep.
And I will ask you how the graph would change its shape and all that.
Will you curve the class, the overall grade?
Okay, that's a very good question. I get it every year, every semester. So first, we have to understand the concept of curving, right? Since we are doing data mining, that means you have a model of a curve and you want to fit your data to learn that parameter of the curve. But we do not have that many data set to help us to understand how the curve should be. And also, I don't think curve is a good idea. But I will adjust the break, the point break.
The threshold for every grade, like A and A, B, B minus, B plus.
Well, we have that on the syllabus,
okay.
but eventually I might adjust them.
Okay.
Just because I don't want two people that have very, very similar grade and one is A minus, the other one is B plus, right? If you are only 0.1 or 0.2% away, I want you to be in the same category.
Oh, okay.
But the bonus, we do have lots of bonus for your final project. Make sure you do it well. The comprehensive exam is not easy, so that's why we don't have that much. We don't put a lot of percentage for the comprehensive exam. It's only 17%. It's not a lot. It's not a lot, but it's not something that you can ignore as well, right?
So it will basically cover all the materials, including link analysis and web advertising, right?
Yeah.
Okay.
Everything in the past 4 months. So someone was asking that memorizing stuff. Can you give me one example?
I can't really find it from.
Right. What do you mean by memorizing?
Well, for example, there was one question in our quiz 11, I guess. Let me just pull it out. That's our latest quiz of 12. For example, explain if the question is to solve m times v equals to v in page rank, what are those two methods? and then some.
That's not memorizing. You have to know how to solve them, right? What are the two methods that you can solve them? Even if you don't even if you don't use the ones that we teach in class, if you have other method to solve them and you will be able to come up with the complexity, I'm okay. But my question is usually ask you, what are the two things that we teach in class?
Okay. Yeah, I just can't think of one very concrete example.
Right. So there's no question that you have to really.
Yeah, I'm just being paranoid.
You should. It's not easy. But we do have people have answer every question correctly, 100%.
Because you keep saying that all the time from when we started this semester, you keep saying that the quiz is not easy. So I'm
The
just-
exam is not easy. The quiz is super easy.
yeah, I'm saying the exam.
Yeah, the exam is not easy.
Are
Is
they
it
gonna
better
be-
that I tell you it's easy? Probably not.
No.
I mean, to be fair, I would say that graph you drew of like the difficulty of homework assignments, not, I mean, yeah, the third one was super hard, but like, I don't think it tapered off as much as you said.
Oh yeah? You don't think
Um,
4, 5, 6 is 6 is
I think-
basically easier, much easier than 1, right? If you look at the grading criteria.
I guess I haven't looked at 6 yet, but
Okay.
It
You
looks
should,
fun.
because you need to apply for that Twitter API token. You should do that as soon as possible.
Okay.
and then so wait, more about the exam. Should we expect a lot of questions like the one you showed us in class, where you would choose like all that applies?
Oh, let me just give you one example. I will ask you to calculate the betweenness of an edge for a simple graph.
Okay.
That would be super easy, right? Because you should know how to calculate betweenness. And if the graph is not huge, this is pretty much just give you the mark.
And you're saying in the exam?
In the exam.
Okay.
Will we be asked to have our cameras on?
No, we cannot do that. But we are going to use the browser that prevents you to open anything else.
But then, so if we had a question, how would we like communicate with you?
You cannot have a question.
Okay. What if
I tried this. I
decide?
tried this exam many times, so it should be good.
Okay.
Can we
Usu-
talk about the
Usually,
final
if you want,
project?
Hmm?
Excuse me. Can we talk about the final projects?
sure.
So remember you said we'll get full points for the final project if the RMSE is better than our TA's RMSE, right? But
Right.
what if it, my implementation doesn't give a better result than TA's? So
Then you try harder to beat the TA.
What?
I mean, is will you
I don't understand.
consider partial credits for that?
We used to have partial credit, but I
But-
don't think your TA is that difficult to beat this semester.
Okay.
Okay, you're looking at this wrong. You should think about how you would be able to beat the TA and get the first place in class, because that's like 4% or 3% bonus for the entire class. That's a lot. And we don't limit you from using any of the libraries. So you can use any Spark machine learning libraries.
Okay. Got it.
I think the real question is you should ask your TA to announce their when they will be announcing their
RMSE.
RMSE.
result. Yeah, because
Okay.
I told them the latest they can do it would be 1 week before project is due, right? But if they like, they can release it earlier.
Okay. So
The
it's really
problem
up
of
to
that
TA.
is people will stop to improve their recommendation system once they beat the TA. Then it makes no sense.
Okay, I see that. Yeah. I have another question on the homework 6. I don't know if we're supposed to answer that question, but do you mind I share my screen?
Sure.
So can you see the graph right now?
Yes.
Can you briefly talk about, explain the figure 2 right here a little bit? Because
Let me see.
so yeah.
Prism can be found at the stream lecture slide. You want to find proper. Where is the text that talk about figure 2?
I think we're supposed to use this
Oh, this is
gender
6.
stream.
This is
Yeah,
assignment
homework
6,
6.
not. Okay.
Yeah. So we're supposed to use this file to generate a stream.
Right.
I think that works like a simulation, right? And
Right.
then so let's suppose this is a simulation stream, and then
Right.
we need to like give it a like extract the sum of the elements out of the stream and then call it a window, and then
Right.
we apply the IFRM algorithm on that window.
Right.
So like do you have any advice how should we get started? Like what is a good I don't know if there's a package to use to.
Well, in this case, you are going to implement the algorithm based
Yeah, I know,
from
but
that stream. So,
I need to read from the stream. So, and that stream is not actually a file, right?
right.
That's
But
something.
if you look at the execution detail, then you have this SSC that will be able to help you. Oh, go up
Sorry.
here.
Oh, this
You
one?
have the stream context, right?
Yeah.
You can set the batch duration, and that's the window. Then you have the context that you can start to work on.
So this is like the Spark context, like the RDD thing.
This is the stream context. This is Spark streaming. So I think to understand this, you have to look into Spark streaming to see how you will be able to use Spark streaming to consume streams and create windows and then implement the algorithm.
Oh, okay. Okay, thank you. Oh,
Sure.
yeah, I'll think more about this. Yeah, that's basically all my question.
This one's super easy. Okay. Any more questions, guys?
No, I think that's pretty much it for today.
Okay. All right. This concludes my last office hour at USC. Thank you, everybody. And I will see you next Monday. Make sure you prepare for your exam.
Thank you.
Thank you.
Have a good weekend.